So today we're talking about Module 5, which is STP, Spanning Tree Protocol Concepts. So this topic is going to cover the causes of loops in a layer 2 network and briefly explain how Spanning Tree Protocol works. So redundancy, as you know, is an important part of the hierarchical design for eliminating single points of failure and preventing disruption of service to our end users. However, redundant networks require the additional physical paths. But logical redundancy must also be a part of the design. So having those alternate physical paths for data to traverse the network makes it possible for users to access network resources despite path disruption. So redundancy is always going to be a good thing. However, in a switched Ethernet network, this may cause both physical and logical layer 2 loops. So in Ethernet LANs, we require a loop-free topology with a single path between any two devices. So a loop in this scenario can cause continued propagation of Ethernet frames until a link is disrupted and breaks that loop. So Spanning Tree was developed. It is a loop prevention network protocol that allows for redundancy while also creating a loop-free layer 2 topology. So it will logically block physical ports in a layer 2 network, preventing frames from circling the network forever. So it compensates for a failure in the network by recalculating and opening up those previously blocked ports if another link were to go down. So path redundancy provides multiple network services by eliminating the possibility of a single point of failure, which we know is always a great thing. However, when multiple paths do exist between two devices on an Ethernet network, and remembering that Ethernet is shared medium, there is no spanning tree implementation on the switches, then a layer 2 loop can occur. A loop can result in MAC address table instability, link saturation, and high CPU utilization on switches as well as your end devices, resulting in the network becoming unusable. So layer 2 Ethernet does not include a mechanism currently to recognize and eliminate endlessly looping frames. Both 4 and 6 do include a mechanism that limits the number of times a layer 3 network can do this, that TTL that we've spoken about before, but not in a layer 2. When these fields are decremented to 0 within that TTL, a router will drop that packet. Ethernet and Ethernet switches, however, have no comparable mechanism for limiting the number of times a switch transmits a layer 2 frame. So STP was developed specifically as a loop prevention mechanism for layer 2 Ethernet. So again, without STP enabled, layer 2 loops can form, causing broadcast, multicast, and unknown unicast frames to loop endlessly. This can bring down a network quickly. When a loop occurs, the MAC address table on a switch will constantly change with the updates from the broadcast frames. This will result in that MAC database being very unstable. So this can also cause very high CPU utilization because now, think about what a broadcast actually does, right? It's a one-to-many. So a switch will get it and push it out every port that has something connected to it except the ingress port. That switch will propagate it and send it to another switch, which could send it to another switch, and so forth and so on, and just endlessly send this information. Same thing with multicast and unknown unicast. Remembering that an unknown unicast is a unicast, so it is going to one destination, except that destination is unknown. And so when a destination is unknown and not in a MAC address table, then again, it acts as kind of a broadcast, and it gets sent out to everyone that is attached to it or to a port on the switch, except again for the ingress. So a broadcast storm we've spoken about before. It's an abnormally high number of broadcasts overwhelming your network during a specific amount of time. They can disable a network within seconds by overwhelming your switches and your end devices. They can be caused by a hardware problem such as a faulty NIC or from a layer 2 loop. Layer 2 broadcasts in a network such as ARP requests are very common. So layer 2 multicasts also are typically forwarded the same way that a broadcast is by your switch. IPv6 packets are never forwarded as a layer 2 broadcast. So ICMPv6, Neighbor Discovery, uses layer 2 multicasting. A host caught in a loop is not accessible to other hosts on the network. Additionally, due to the constant changes in the MAC table, the switch also does not know out of which port to forward unicast frames. So to prevent these issues from occurring in a redundant network, some type of spanning tree must be enabled on the switches. It is enabled by default on Cisco switches to prevent layer 2 loops from occurring. So STP is based on an algorithm invented by Radia Perlman while working for Digital Equipment Corporation and published in a 1985 paper called An Algorithm for Distributed Computation of a Spanning Tree in Extended LAN. Her spanning tree algorithm, referred to as STA, creates a loop-free topology by selecting a single root bridge where all other switches determine a single least cost path. It prevents loops from occurring by configuring a loop-free path through the network using strategically placed blocking states or blocking state ports. So switches that are running STP are able to compensate for failures by dynamically unblocking those same ports when it detects that a link has gone down, and then again permitting traffic to traverse the alternate path until perhaps the other link comes back up, and then STP will recalculate and possibly block down the port that was previously blocked. So how does it create this loop-free topology? It selects a root bridge. This bridge, which is a switch, is the reference point for the entire network to build a spanning tree around. So referred to, think of it as the root of the tree. When switches first start up, every switch is going to think it's the root bridge, and it will send out a message with their priority value. When the switches send out their priority messages, their MAC addresses are also included. The switch with the lowest priority MAC address becomes the root bridge. This again can sometimes be problematic because in older switches, chances are their NIC cards, which is where your MAC address comes from, would most likely be a lower number than something that is recent. So a very old switch could eventually or essentially take over and become the root bridge. So how does it block redundant paths? It ensures that there is only one logical path between all destinations on the network by intentionally blocking a redundant path that could cause a loop. When a port is blocked, user data is prevented from entering or leaving that port. Okay? It also creates a loop-free topology. So a blocked port has the effect of making that link a non-forwarding link between the two switches. This creates a topology where each switch has only a single path back to that root bridge. This is similar again to branches on a tree that connect to the root of that tree. Then it has to recalculate the case, or in the case of a link failure. So physical links still exist to provide redundancy, but these paths are disabled to prevent those loops from occurring. So if the path, so don't forget, when we're talking physical and logical, this logical blocking is something that happens in software. You still have that physical connection where redundancy would be in place if that other link went down. So if the path is ever needed to compensate for a network cable or a switch failure, STP would simply recalculate the path and unblock the necessary ports to again allow the redundant path to become active. So the calculations can occur anytime a new switch or new timer switch link is added to your network. So using the STA, STP builds a loop-free topology in 4 steps. First, it's going to elect the bridge. After it elects the root ports after the bridge, which are ports that lead directly to that root bridge. Each designated port, which are ports that do not lead to the root port, or then it's going to elect designated ports. These are ports that do not lead directly to the root port. And then it will elect alternate blocked ports. So the process is, during the algorithm and the STP functions, switches will use a bridge protocol data unit to share information about themselves and their connections. BPDUs are used to select or elect the root bridge, the root ports, the designated ports, and the alternate ports. Each BPDU contains a bridge ID that is going to identify which switch sent that message. The BID is involved in making many of the STA decisions, including root bridge and port roles. The BID contains a priority value, the default of which is 32768 in Cisco switches, and the MAC address of the switch, as well as an extended system ID number, which is the number of the VLAN that it's being sent from. So the lowest BID value is determined by the combination of these 3 fields. I would use the show spanning tree to see this information. So as an example, if I don't change the priority, so we can change the priority as admins, if I do not change the priority, the default value of 32768 plus the default VLAN of 1 would be added together to give me a new priority of 32769. The bridge priority is the default priority value for all Cisco switches, which is 32768. The range is 0 to 61440 in increments of 4096. A lower bridge priority is preferable. So if I go in there and I assign my bridge a priority of 0, it will take precedence over all the other bridges priorities. So we can use a command to force the bridge port election. Then you have the extended system ID. This is a value, it's a decimal value added to the bridge priority, and it is the value that identifies the VLAN for this BPDU. The MAC address is assigned by the manufacturer, as you know, so an older switch would likely have a better priority than a newer switch. This again is problematic. Also, when 2 switches are configured with the same priority and have the same extended system ID, the switch having the MAC address with the lowest value expressed in hexadecimal will be considered the lower BID. So how does this all work? The STA designates a single switch as the root bridge and uses it as the reference point for all bridge calculations. So in this slide, you can see that S1, we have changed the default priority value from 32768 to 24577. Now, switches will exchange those BPDUs to build the loop-free topology, beginning with selecting that root bridge. All switches in the broadcast domain participate in this selection. So after the switch boots up, again, all switches begin to send out those frames every 2 seconds. And again, until all other switches start receiving those frames with their information, when a switch generates from the boot state, it always considers that it is the root bridge right from the get-go, until it starts receiving all the BBTUs from the other switches. These frames contain the BID of the sending switch and the BID of the root bridge known as the root ID. Again, the switch with the lowest BID will become the root bridge. At first, again, all switches declare themselves as the root bridge with their own BID set as the root ID. Eventually, the switches will learn through the exchange of those BBTUs which switch has the lowest BID and will agree on one root bridge. If all your priorities match, it will be the switch with the lowest MAC address that would be selected. So if switch 1 were to go down, the other bridges, because they all match, the other two in this example, would have to go with the lowest MAC address. So if switch 1 were to go down, then switch 2 would become the new root bridge because its MAC address is less than that of switch 3. Now, because of the default BID of 32768, it is always possible for two or more switches to have the same priority. In this scenario where the priorities are the same, the switch with the lowest MAC address will become the root bridge, unless we manipulate something. So by default, our devices acting without our interplay will do it this way. The administrator should configure the desired root bridge switch with a lower priority, as you see here. So in this figure, by default, all switches would have the same priority of 32769, meaning the default of 32768 plus the VLAN default of 1. So if the administrator didn't change the priority on S1, it would default to the lowest MAC address. In this case, without the interference of an administrator changing the priority on switch 1 to 24577, then the priority would be 32769 for both, and switch 2 would become the root bridge. So the value is based on, again, the 32768 default bridge priority and the extended system ID of VLAN 1. When the root bridge has been elected for a given spanning tree instance, the algorithm starts determining the best paths to get to that root bridge from all destinations in the broadcast domain. The path information, known as the internal root path cost, is determined by the sum of all the individual port costs along with the path from the switch to the root bridge. So when a switch receives the BPDU, it adds the ingress port cost of the segment to determine its internal root path cost. The default port costs are defined by the speed at which the ports operate. So the table here shows the default port costs suggested by IEEE. Cisco switches by default use these values as defined in IEEE 802.1d, also known as the short path cost for both STP and RSTP. Although switch ports have a default port cost associated with them, we again can change it to something that we want to force the election on. The ability to configure individual port costs again gives us the flexibility to manually control the spanning tree path to the root bridge. So here, 10 gigs, cost of 2, in STP, cost of 2,000, 1 gig, cost of 4, and a cost of 20,000 in RSTP. 100 megs is 19, 10 megs is 100. Now, in earlier STP, there was no distinction between the cost of a 1 gig port and a 10 gig port. This created lots of problems, and you'll talk about that more as you go along and learning about certain protocols, especially routing protocols. So different methods had to be put into place in order to recognize that 10 gigs was a lot larger than 1 gig. And you'll learn more about that as you go along. So that's just a little side note for you to keep in the back of your bonnet. So after my root bridge has been determined, Now the algorithm is used to select the root port. Every non-root switch will select one root port. The root port is the port closest to the root bridge. So just visually on S2, can we all see that the port of F01 is the closest to S1? So that will be the root port on S2. Likewise, on S3, you can also see that F01 is a direct connection to S1. So on S03, FA01 is also designated as your root port. Okay, so step 2 now complete. So this overall cost is known as the internal root path cost. The internal root path cost is equal to the sum of all the port costs along the path to the root bridge as shown in the figure. Paths with the lowest cost become preferred, and all other redundant paths will be blocked. So in this example, the internal root path cost from S2 to the root bridge of S1 over path 1 would be 19. So we're, for example, or for the purpose of this example, are saying that all of these paths are a cost of 19. So path 1 is going directly from FA01 on switch 2 to FA01 on switch 1, and it has a cost path of 19. If I were to go via path 2, okay, I would go from here to here for 19, and then through here for another 19. That would be a cost of 38. So with that in mind, because path 1 has a lower overall path cost to the root bridge, it is the preferred path, and F0 becomes the root port on switch 2. Now, every segment between the two switches will have one designated port. Your designated port is a port on the segment that has the internal root path to the cost bridge. The designated port has the best path to receive traffic leading to the bridge. So, you can see in the example that all ports on the root bridge are designated because they are leading directly to the root bridge. So these are already your designated ports. And that is because this is the root bridge. Now, if I'm going from S2 to S1, S1, then you can see the direct line from S2 to S1 is F0 on switch 1. So it is the designated port. Likewise on S3, the direct connection to go through and to get to S1 is F02 on S1. So that is your designated port. What is not a root port or a designated port becomes an alternate or blocked port. So you would see this when redundant links are attached. So again, if S2 were to take an alternate path, to get to S1, it would go through F02. So that would be on the path to get to the root bridge. So that is also defined as a designated port. Also, if one end of a segment is a root port, the other end is automatically a designated port. All ports attached to end devices are also designated ports. On segments between two switches, where neither of the switches is the root bridge, the port on the switch with the least cost path to the root bridge is a designated port. Now, if a port is not a root port or a designated port, then it becomes the alternate or the backup port. So here you see that S3 FA02 is your alternate port or your backup port. Alternate ports are in discarding or blocking states to prevent those loops from happening. So in this figure, the algorithm has configured port 2 on S3 in the alternate role. Port 2 on S3 is in the blocking state and will not forward Ethernet frames. All other inner switch ports are in the forwarding state. This is how the loop prevention part of STP works. When a switch has multiple equal cost paths to the root bridge, the switch will determine a port using the following criteria: the lowest sender BID, the lowest sender port priority, the lowest sender port ID. So lowest sender ID. This topology has 4 switches, with switch S1 again as your root bridge. Port F01 on switch 3 and port F03 on switch 4 have been selected as root ports because they have the root path cost to the root bridge for their respective switches. S2 has 2 ports. F01 and F02, they have equal cost paths to the root bridge. So the bridge ID of 3 and 4 will be used to break that tie. This is known as the sender's BID because they have to travel through either switch 3 to get to the root port or switch 4 to get to the root port from switch 2. S3 has this following BID of 32,769 with all 5s, and S4 has a BID of 32,769 with all 1s. So because S4 has a lower BID, the F01 port of S2, which is the port connected to 4, is the root port. It will then shut down access to the F02 port and make it an alternate port, again blocking that loop. So lowest end of priority. This topology has 2 switches which are connected with 2 equal cost paths. S1 is the root bridge because of its lower BID, so both of its ports are automatically designated. It's the nature of a root bridge. So the first step is a tie. Next, the sender, who is S1, its port priority, the default port priority is 128, as in this example. So both ports on S1 have the same priority. This is also a tie. However, if either port on S1 was configured with a lower port priority, S4 would put its adjacent port in the forwarding state. The other port on S4 would be in the blocking state. So the lower sender port ID, the last tiebreaker is the lower sender's port ID. So as you can see, again, S1 has 24577 as its beginning point. S4 has received BBTUs from port F01 and F02 on switch 1. The decision is based on the sender's port ID, not the receiver's ID. So because the port ID of F01 on S1 is lower than the F02, the port F06 that is attached to F01 will become the root. Okay, so again, because I have 2 redundant paths, F01 has the lowest BID number. So because it has the lowest BID number, you look to the adjoining port on switch 4, and that is the one that becomes the root port. Okay, if I'm not a root port or a designated port, I am an alternate or a blocking port, which is why port 5 on S4 is an alternate port in the blocking state. Now, STP convergent requires 3 timers as follows. Your hello timer, which is the the interval between BPDUs. The default is 2 seconds, but it can be modified to between 1 and 10 seconds. Then you have your forward delay timer. This is the time that is spent in the listening and learning state. This has a default of 15 seconds, but can also be modified between 4 and 30 seconds. The maximum age timer is the maximum length of time that a switch waits before attempting to change the STP topology. Your default, again, is 20 seconds, but can be modified between 6 and 40. So in a production network, your timers are very important because when we add up all of the time, if a link fails, that's the time it's going to take where it's going to be idle and not be transferring any data whatsoever. So we may want to manipulate these times to force the backup link to activate sooner than the default time. Again, the default times can be changed on the root bridge, which will dictate the values of these timers for the whole entire STP domain. Now, STP facilitates the logical loop-free path throughout the broadcast domain. The tree is determined through the information learned by the exchange of those BPDUs between the interconnected switches. If a switch port transitions directly from the blocking state to the forwarding state without information about the full topology during that transition, the port can temporarily create those loops. For that reason, STP has 5 port states that it follows, and you need to know what they are and the order in which they occur. The disabled state is considered non-operational. So again, my blocking state, you have no BBDUs being received. It is a maximum age of 20 seconds. Within your listening state, it is a forward delay of 15 seconds. Your learning has a forward delay of 15 seconds before you actually transition to that forwarding state. So, blocking will be in a blocking state until the STP determines if the port is a root port or a designated port. So if we added up the timers in this example, it would be a total of 20 plus 15 plus 15, which would equal 50, so that it would be a 50-second delay before that port could send any data using the default values of blocking, listening, and learning. So the table here summarizes the operational details of each port state. In blocking, I receive those frames. My MAC address does not get updated, and my port cannot forward data. In the listening, I can both receive and send. Again, I'm still not updating my MAC address table, and I am still not forwarding frames. In the learning state, I am still receiving and sending, and now because I'm learning information about my directly connected neighbors, I am starting to update my table, but I am still not forwarding data frames. In the forwarding state, I am still receiving and sending. I'm also updating table on what I'm receiving, and then I become in the forwarding state. If I am disabled, I am neither sending or receiving, nor am I updating, nor am I forwarding frames. I am totally disabled and non-functional. So STP can be configured to operate in an environment with multiple VLANs. So in a per VLAN spanning tree, PVST, there is a root bridge elected for each spanning tree instance. This makes it possible to have different root bridges for different sets of VLANs. So STP operates a separate instance of STP for each individual VLAN. If all ports on a switch are members of VLAN 1, as we know is the case by default, then there is only one spanning tree instance. The more instances of spanning tree that we have, the more memory and processing power is also needed. In other versions of STP, we can group VLANs together so that they can use the same calculation. This is also helpful for utilizing all ports. They can have different states for different VLANs. They can also be active for one and inactive for another. Many professionals generally use spanning tree and STP to refer to the various implementations of spanning trees, such as rapid spanning tree protocol and multiple spanning tree protocol. In order to communicate spanning tree concepts correctly, it is important to refer to the implementation or standard of the spanning tree in its context. So the latest IEEE documentation, which is 802.1D-2004, says STP has now been superseded by Rapid Spanning Tree Protocol, or RSTP. The IEEE uses STP to refer to the original implementation. RSTP is used to describe the version of spanning tree specified in IEEE 802.1D-2004. Because the two protocols share much of the same terminology and methodology for loop-free paths, the primary focus will be on the current standard in the Cisco proprietary implementations of both. Cisco switches running iOS 15 or later can run per VLAN spanning tree by default. This version will incorporate many of the specifications of IEEE 802.1d-2004, such as alternate ports in place of the former non-designated ports. Switches must explicitly be configured for rapid tranning speed mode in order to run the rapid tranning speed protocol. In the network, all switches must run the same version of STP and will default to the lowest version. So if there were a switch only capable of STP, it could not run PVST and the newer. So capable switches would default always to the lowest, which again, not optimal. So different variations. STP, you can go ahead and read all these. Starts with STP, which is the original version of IEEE 802.1d from 1998. It provides a loop-free topology in a network with redundant links, also called common spanning tree. It assumes only one spanning tree instance for the entire bridge network, regardless of how many VLANs you have. PVST is a Cisco enhancement. It provides a separate 802.1d spanning tree instance for each VLAN. It supports port fast, uplink fast, backbone fast, BBTU, BPDU filter, root guard, and loop guard. 802.1d 2004 is an updated version of STP incorporating IEEE 802.1w, which is RSTP. So RSTP, or IEEE 802.1w, is an evolution of STP that provides faster convergence than STP. And I know I just said I wasn't going to read these, but apparently I am. Rapid PVST is a Cisco enhancement of RSTP that uses PVST and provides a separate instance of 802.1w per VLAN. So each separate instance supports port fast, BPDU guard, BPDU filter, root guard, and loop guard. MSTP, Multiple Spanning Tree Protocol, is an IEEE standard inspired again by the earliest Cisco proprietary MST. MSTT maps multiple VLANs into the same spanning tree instance. And then MST is the Cisco implementation of MSTP, which can provide up to 16 instances of RSTP and combines many VLANs with the same physical and logical topology into a common instance, which also supports port fast, BPDU, guard, and BBDU filter, root guard, and loop guard. So RSTP, IEEE 802.1w, supersedes the original of 802.1d while retaining backward compatibility, so it will work with the older version of STP. Users that are familiar with the original STP can easily configure RSTP. The same spanning tree algorithm is used for both to determine port roles and the topology. RSTP increases the speed of that recalculation, however, of spanning tree when the layer 2 network topology changes. We want to get away from that 50 seconds that we learned about earlier, which causes loss of data not being able to be forwarded. So it can achieve much faster convergence in a poorly configured network, sometimes in as little as a few hundred milliseconds. If a port is configured to be an alternate port, it can immediately change to a forwarding state without waiting for the network to converge. As a note, Rapid PVST is the Cisco implementation of RSTP on a per VLAN basis, with Rapid PVST an independent instance of RSTP running for each VLAN. You won't see those until either a little later or possibly not even until an upper level networking course. So within RSTP, and as opposed to STP, There are only 3 ports in RSTP: the discarding, the learning, and the forwarding. So the 802.1d disabled blocking and listening states are all merged into the 802.1w discarding state. So all merged into one. Your learning mirrors your learning. Your forwarding mirrors your forwarding. With regard to your ports, root ports and designated ports are the same for both. However, there are 2 RSTP port roles that correspond to your blocking state. In STP, a blocked port is defined as not being the designated or the root port. RSTP has 2 port roles for this purpose. So if you see output with ports defined as backup or alternate, you are running RSTP. So in this instance, these 2 are mirrored, and this one breaks out into 2 different states. Now, the alternate port has an alternate path to the root bridge. However, your backup port is a backup to a shared medium such as a hub. A backup port is less common because hubs are now considered legacy devices and pretty much obsolete. So that is the difference between the alternate port and the backup port within RSTP. Now, port fast in BBTU. I always say, it sounds like I'm saying T, but I'm saying D. BPDU guard. When a device is connected to a switch port, or when a switch powers up, that port goes through both the listening and learning states, each time waiting for that forwarding delay timer to expire. This delay is 15 seconds for each state for a total of 30 seconds. So this can present a huge problem for things like DHCP, where clients are trying to discover a server, and this is because the DHCP process may time out. The result is that the client will not receive a valid IP4 address. So things that we can implement to push that forward. We can configure a port with port fast. That port that is configured with port fast would then transition directly from a blocking state to a forwarding state, immediately avoiding that 30-second delay. You only use port fast on access ports to allow devices connected to those ports to access the network immediately. So again, port fast should only be used on access ports. If you were to enable it on a port connecting to another switch, you risk creating a spanning tree loop. So a port fast enabled switch port should never receive BPDUs because that would indicate that the switch is connected to the port, potentially causing that spanning tree loop. Cisco switches also support a device called, or a feature, excuse me, called BPDU guard. So when this is enabled, it will immediately put the switch port in an error disabled state upon any receipt of that BPDU, therefore preventing those loops. So it protects against those potential loops by effectively shutting down that port. If that happens and the port goes into error disabled, the only way that that port can come back up is we have to go back into it and manually do a no-shut command on that port. So it is an added protection to prevent from creating those loops. Over the years, organizations required greater resiliency and availability in their LANs. Ethernet LANs went from a few interconnected switches connected to a single router to a very sophisticated hierarchical network design, including access, distribution, and core layers. Depending on the implementation of this, Layer 2 may include not only the access layer, but also the distribution layer or even the core layer. These designs may include hundreds of switches with hundreds or even thousands of VLANs. STP has adapted to the added redundancy and complexity with enhancements as part of the RSTP and MSTP. An important aspect to network design is fast and predictable convergence when there is a failure or a change in your topology. Spanning tree does not offer the same efficiencies and predictabilities that is provided by protocols at the layer 3. So layer 3 routing allows for redundant paths and loops in the topology without actually blocking any ports. For this reason, some environments are transitioning to layer 3 switching everywhere except where devices connect to the access layer switch. The connections between access layer switches and distribution switches would be layer 3 instead of layer 2. This can be done utilizing the no switch port command from an earlier module. So, spanning tree again can be one of those concepts that can be a little tough to get, and it really is just going through and testing yourself and understanding the port structure, how they're assigned, and the subtle differences between all the different instances.